Agree? All right. So this is I1, remember. Okay? So now, if I just separate I1 from this, phi to 1 is going to be mu naught over 4 pi, the integral over C2 over a closed curve, the integral over C1 over closed curve of dl1 dotted dl2 over the magnitude of r minus r prime times by I1. And as you can see here, this is just simply the property of the two conductors. All right. It depends on the distance between the two conductors and the shape of the two conductors. Sometimes if it's not in free space, this is going to change the magnetic permeability. So it's just purely a geometrical property of the conductors. And when you do the integration for out, what you get is the constant, which depends on the property of the conductors. So we call that conductors, that constant, we call it inductance. In this case, it's called mutual inductance. It's between two conductors. So I will call it phi to 1 is equals to M1 times I1. Where M1 is equal to mu naught over 4 pi, the integral over C2, the integral over C1, dl1 dotted dl2 over the magnitude of r minus r prime. Now, instead of we considered here the B field of this on that one and flux through this, let's do the reverse. So you can imagine that you have a current here I2 and you want to find the flux through this loop. What would you guess that you find? You find, I will give that one to you, so I will call it that one, the flux through 1 due to 2, and that is going to be M1, 2, and it should be I2, right? So what would you expect for M1, 2? Just following the same procedure, you find mu naught over 4 pi, the integral, now the order is going to switch, as long as you keep the distance the same, this doesn't change. So the only difference that would change is the order of the integration, which doesn't matter. So C1 over a closed curve, C2, dl2 goes to dl1 over magnitude of r minus r prime, or r prime minus r. So M1, 2 is the same as M21. It's called mutual inductance. Inductance of the two conductors. So there is a self-inductance if you have just only one conductor involved. Like for example, if you have, forget this one, and just only consider the current through this. And if you want to find the self-inductance of this, all you have to do is just find the magnitude magnetic field due to this current, and we use that magnetic field to find the flux through this, and that flux is going to be proportional to the current, and the proportionality constant, and instead of M, it's going to be L, which is going to be the self-inductance of this conductor. So we'll do examples next time. And it really helps you finding magnetic flux when you have a complicated geometry.